Okay, so it looks like most of you are done with the graph. So I asked you specifically to make an XY table so that you could actually get some points, so that when you went to graph the inverse, you would have points to reference off of. And a lot of you did do the XY table, but then you only looked at positive values. So I did point out, make sure to try some negative values. So most of you did 0, and anything raised to 0 power is always 1, right? If you did 1, you get 2. If you did 2, you get 4. But on the negative side, if we put in, say, -1, that gives us what? 1/2. And if we plug in -2, that gives us 1/4. Okay, and so we talked about before, does it matter how far to the negative you go? Will you ever reach 0? No, it gets smaller and smaller and smaller. Okay, and so rather than solving for the inverse and trying to graph that, I just wanted you to invert the points that you got from this one. And so keeping in mind, if we had 0, 1 here, the inverse would be 1, 0, right? For this point back here, for -1, positive 1/2, we would have 1/2 positive, -1. Okay. And so if we keep going like that, again, these points over here, they never reach 0. So what's going to happen to these points as we get closer to the y-axis? Will they ever reach 0? No. They don't either. Okay, so talking about the domain to begin with, let's talk about the graph of f of x, just 2 to the x power. What is the domain on it? Are there any restrictions on x? No. So we would state that as -infinity to +infinity. Okay, how about the range? 0 to +infinity. Okay, so talking about the inverse of it, yes, City? Well, will it ever reach 0? No, never. Yeah, so even if you had x as -10,000, it's still going to be 1/2 raised to something positive, right? So it'll never reach 0. Okay, so for the inverse, what happens to the domain? 0 to infinity. And then how about its range? -infinity to +infinity. Okay.
If you were to make the equation for the inverse, what would it look like?
Oh, we're going to do that today.
Oh, okay.
Yeah, that's why I wanted to start with this. What is it we're doing? Okay, the other thing I asked you for were asymptotes. On the 2 to the x, is there an asymptote? Yeah, what's the asymptote on that one?
0.
Y equals 0. Yes, we do have a horizontal asymptote at y equals 0. Okay, and, well, actually, it's not really on the right side, right? It's only on the left. So let's not say this because it's not going to follow here, but let's just say on the left. So when x is less than 0, we'll have one at y equals 0. Okay. And then for the inverse of it, what happens here?
The asymptote is x equals 0.
Yeah, but only, yeah, so only when y. So when y is less than 0, we get x equals 0. Okay. Alrighty. So just kind of wanted to start here to think about the relationship because today's lesson is on logarithms. So hopefully now we'll answer your question, Daniela. Okay. All right, so what we just looked at was f of x equals 2 to the x power and its inverse. The inverse function that we just looked at is a logarithm. It's a logarithmic function. So in other words, we had f of x is equal to 2 raised to the x power. The inverse function, f inverse of x, is equal to log base 2 of x. That is the function. And we already talked about the domain for 2 to the x was negative infinity to positive infinity. And the range for it was 0 to positive infinity. And then when we switched and looked at the inverse function, we got 0 to infinity for the domain and negative infinity to positive infinity for the range. Does anybody see the relationship between them? They're flipped, exactly. Okay, so let's look more at the log. Right, so we've got this equation here, y is equal to log base b of x. Okay, and so the pieces of it are, you have that b, again, that represents the base of the logarithm. That base has to be positive, and it cannot be equal to 1. And then the x in the logarithm is called the argument of the logarithm, and that term has to be positive. We have a couple special logarithms that we want to recognize. One of them is the common log, and what that is, it's a logarithm with a base of 10. Okay? So usually when we see these, we don't see a base on them. It would be seen as just log of, we'll just say log of x. So it's sort of like when we work with radicals. If we see that radical, what do we understand the index to be?
2.
We understand the index to be 2. So it's the same thing with the common log. If we see a log and no base indicated, it is understood to be base 10. Our other special logarithm is what we call the natural log. And even though it's natural log, it is abbreviated LN, the other way around. Yep. Okay. All right. Good luck. Right. So that would be like natural log of x. And again, it's the same thing as log base e of x. They're equal to the same thing. Yes, Catherine?
Sorry, I can't really see. Does it say like ln?
Yes, ln.
Is the x an exponent, or is it just a regular?
It's an argument.
Oh.
Yeah, it's the argument of it. We could do that. It's the argument of it. All right. So any questions so far? All right. So what we're going to do is make a table. So basically, exponential form and logarithmic forms are just re-expressions of one another, right? It's just a rearrangement of terms, okay? So if you've got, like in the first column, y is equal to b to the x power, we can re-express that as a logarithm, and that would become x is equal to log base b of y, right? So you'll want to notice the special pieces to it here. In the exponent, we have a base of b. That's also the base on the logarithm. In the exponent form, we have b raised to an exponent is equal to y. The equal to portion is the argument in the logarithm. And the last piece, the exponent that the base is being raised to, up here, that's what the logarithm is equal to. Okay. So it is just a rearrangement, a re-expression of the terms from one form into another. And you can go back and forth between, all depending on what it is you're trying to solve. So the first thing we're going to do is just do some rearranging, okay? So in our first one, where we have 16 is equal to 4 squared, and we just want to rearrange that into the logarithmic form. So I have log. The base of my exponent is 4, so therefore that is the base on my log. Log base 4 of the argument is the equal to part, so of 16, and that is equal to the exponent that's on the exponential form. So log base 4 of 16 is equal to 2. In our next one, I have 10 cubed is equal to 1,000. Again, I'm just going to convert it into logarithmic form. So I have a log. The base of my exponent is 10, so that becomes the base of my log. My exponential form is equal to 1,000, so that is going to be my argument. And then this is equal to the exponent on the exponential form equals 3. Yes?
Isn't log base 10 just the...
Exactly. So because this is a common log with the base of 10, we actually do not need to include that base 10 on there. And so we would just turn this into log of 1,000 is equal to 3. So in the next one, we're just going to go in the reverse order. We're starting with the logarithm, right? So we have 4 is equal to log base 3 of 81. We want to put it into exponential form, right? So again, I usually start with the base portion of it. The base on the log is 3, so I know that that's going to be the base of my exponent. The whole logarithm is equal to 4, so 4 is going to become the exponent on my base, and it's equal to the argument of 81. And is that a true statement? 3 to the 4th is 81?
Yes.
Yes. All right. So in the next one, I have log base 2 of 1/2 is equal to -1. So again, I like to start with the base. My base is 2, so it's the base of the exponent. Raised 2, whatever the log is equal to, that's -1, is equal to the argument of 1/2. And again, do we have a true statement there? Yes. And I included one more. Why did I include this one? Okay, because it has a base of e. So keep in mind that natural log is equal to a log with a base of e. Okay. So these two are equivalent. Again, we just use ln as the notation for it, but these mean the same thing. All right, so again, going to my base of e, that's the base of my exponent, raised 2, whatever the log is equal to is my exponent now, and that is equal to 1. And again, do we have a true statement? Yes. Okay, so what do we think so far? Not bad. Okay. Logarithms are actually a lot of fun to work with. Okay, I have got 6 for you guys to try. So it looks like most of you guys have finished. Good job, everybody. Oh, there we go. Unfrozen. Right. So, probably the most common thing I saw was leaving the log base e of 9 in there. So remember, if you see a base e on there, go ahead and turn it into a natural log. And again, and you don't have to erase that step in there. It's perfectly fine to leave that, especially when you are new to doing these. I think it helps writing in those extra steps. On F, again, just keep in mind that natural log is a log with the base e. So I think it also helps to write it out with the base of e when you are rearranging the terms. Okay, so I had the question of, well, what exactly is the log? So logarithms are their numerical values, all right? So do you remember last class how we were solving exponential equations, all right? Well, when we had our exponential equation set up such that, let's say we had 2 to the x power is equal to 8, right? You guys knew how to solve that one, right? Okay, look at D. Look at its re-expression. 3 to the x power is equal to 5. Can you tell me what x is? No. And that's what the logarithm is for, right? So a lot of these you can put into, usually we would only go into a logarithmic form when we're faced with a situation like this. Like 3 to what power is 5? I have no idea. I wouldn't expect anybody here to know. However, we can use a logarithm and our calculators. So back in the old days, calculators didn't have that logarithm function in there where you could calculate it. And they had what was called a slide rule. We'll have to Google one later. Actually, a student brought one in last year. It was kind of fun. It was her grandfather, I think, was a physics major in college, and he kept his slide rule that he used. So these days, all the physics majors walk around with calculators. In those days, the engineers and the physics majors always carried a slide rule to do their calculations. Okay, so again, if we're faced with something like this, wouldn't expect you to know that off the top of your head. We would put it into a logarithm and then evaluate the logarithm in our calculators. Okay, so this part here, the numbers are not so crazy. So these are logarithms that we can actually solve. So again, a logarithm is nothing but a numeric value. Okay. So if you see something like this where it says evaluate the logarithm, it's asking you. It's just like if I said evaluate the square root of 9. You would tell me 3, right? It's the same thing. Evaluate log base 2 of 16. Tell me what that is equal to. So for now, we are new to these, so I wouldn't expect you to just solve this off the top of your head, but we're going to go ahead and think about the exponential form of this. So the exponential form of this would mean that we would have 2 raised to some power, and it should equal 16. Well, what does that power have to be?
4.
Has to be 4. So log base 2 of 16 is equal to 4. Yes?
Do you always, like, write that little watch, or can you write it as, like, X or something?
I was going to do X on the next one, so you see it that way too. Okay. All right. So for the next one, where we have log base 3 of 1 over 27, it is perfectly fine if you want to set it equal to a variable. That works as well too. Okay. And if we re-express this, this becomes 3 to the x power is equal to 1 over 27. All right. Now, if you're looking at this and you're like, I don't quite remember, what homework did we have last class? What were we doing? We were solving these, and that's the whole reason, was preparing for this, okay? So remember that you want to get the bases the same. So this is 3 to the x on this side. 1 over 27 is re-expressed as 3 to the negative 3, which means what does x have to equal? Negative 3. And again, you don't have to do that step if you see that 3 to the x is equal to 1 over 27 and you already know, oh, well, it's negative 3. That's fine. There's no reason to do this step. So here we are here. X is equal to negative 3. So the only thing I want to point out in this one is, if you were to solve it like this, but you didn't put an equal x on here, would that be correct? No, this is incorrect, because as of now, the way this is stated, there is no x in there, so you can't tell me that x is equal to negative 3. So if you are going to use a variable like this to solve, make sure that you tell me that you are making this equal to x. And now it's okay. So I'm just going to highlight these, that make sure those two pieces are in there. Yes, Catherine?
So if we're not using x, can we just use like a question mark or something?
Yeah, that's fine. But then don't say, yeah, don't say question mark is equal to the value. Just go and plug the value back in. Like I did in the first one. Yeah, I just plugged it in right up here. Okay, let's look at our next one. I have log of 100. What does that mean? It's a base of 10, okay? So, and there is no harm restating it as such. So now I have log base 10 of 100. I'll go ahead and throw in a variable over here. So that's like saying 10 raised to the a power is equal to 100. What does a have to be? It has to be 2. So log of 100 is equal to 2. Yes?
So the log of 100 always 2, since it's like restated with base of 10.
Yes. Yep. All right. So in our next one, I have log base 4 of 2. Okay. So again, that's like saying 4 to the, I heard you say, could I put a question mark in? Sure. 4 to what power is equal to 2? And do we know that already, or do we want to set it up as an exponential? Exponential? Okay. So remember, you'd have to have this as the same base. I'm going to go ahead and change that to an x because it's easier to work with that than a question mark. So this is like having 2 squared raised to the x power is equal to 2 to the first. And then solving the exponents now, 2x is equal to 1, which means x is equal to 1/2. So log base 4 of 2 is equal to 1/2. How are we doing with these logs so far? They're not so bad, right? Okay. I have log base 81 of 9. So again, the base of the log is the base of the exponent. So 81 raised to what power would give us 9? To 1/2 power, exactly. Okay, and our next one here. I have log base 5 of 5. Yes, 5 raised to what power would give us 5? That's going to be 1. Okay. So now I'm going to ask you, what if I asked you for log base 1000 of 1000? It's 1. What if I asked you for log base 72 of 72? 1. Okay. Log base 1,000,000 of 1,000,000 is still 1. This is one of the log properties that we want to remember. Log base b of b. So if your base is the same as your argument, what will the log always be equal to? 1. So I want to remember that property. And our last one, log base 12 of 1. Yeah, because I have to do 12 to what power will give me 1? Has to be 0. So along the same lines as we were looking at earlier, what happens if I asked you for log base 1000 of 1? It'll be 0. Okay, so that's another property that we want to remember. If you have log base anything of 1, it will always, always, always be equal to 0. Okay, so those are two properties. And again, when you're working with these a lot, you remember those properties pretty quickly. But when you're just beginning to learn them, as long as you can remember how to rearrange the logarithm to an exponential form, can you always figure these properties out? Always. Okay. So don't spend time trying to just memorize properties, right? Just make sure that you understand the relationship between the exponential and the log, and then you'll always be able to solve. Okay. So we're going to look at some log equations here. So this time we have the unknown variable inside the argument, and we want to figure out what that is. So in our first one, I have log base 5 of x is equal to 2. So I'm going to take it out of the logarithm and put it into exponential form. Right? So again, the base of the log becomes the base of the exponent, and we raise it to the second power because that's what the log is equal to, and that should be equal to the argument, which means, what is our argument here? 25. All right. In our next one, log base 3 of 2x minus 1 is equal to 2. So again, I need to figure out what x is, so I'm going to undo this logarithm and put it into exponential form. I have a base of 3 on my log, so again, that's going to be the base on my exponent, raised to the second power, because that's what my log is equal to, and it's equal to the argument, and this time the argument is 2x minus 1. And now do we have a nice equation that we know how to solve? Yes. So we get 9 is equal to 2x minus 1, which means we have 10 is equal to 2x. What is x in this case? 5. X is equal to 5. Alrighty. So if we do a quick check, we're going to get log base 3 of 5 times 2 is 10 minus 1 is 9. And is that indeed equal to 2? It is. Okay. All right. So our next one, log base 3 of x squared is equal to 2. So again, I need to solve for that x, so I'm going to get it out of there by putting it into exponential form. So the base of my log is 3. So I have 3 raised to the second power, because that's what the log is equal to, equals x squared is my argument. So that means I'm going to have 9 is equal to x squared. So x is equal to 3. Okay, technically we would have, actually what? Technically we have plus or minus 3. This is one we'll have to be careful with. If it's left in this form and we go to check it, are both answers going to work?
No.
Huh. If we square? Because what did we say? We can't ever have a negative argument, right? Okay, but right now in this format it's squared. So if it were negative 3 and we squared it, it would work. This one is a little bit funny because we're going to run into a couple situations. So actually I'm going to go ahead and just stick with the positive here. Because, let's see, you have a quiz next class, but the class after we're going to look at other properties, and it kind of undoes this one. Yes?
Could you just do the square root of the square root of x squared?
Yeah, yeah, that's true. Yeah, that's fine too.
Is this on the quiz?
No, the logarithms will not be on the quiz. They'll be on the second quiz. All right. Okay. And this one here. Log base 4 of x squared minus 3x, all of that equal to 1. So again, I want to get those x's out of the argument. So I'm going to convert this to an exponential. I have a base of 4 there, so that becomes the base of the exponent. And what am I raising that exponent to? 1. And that's equal to the argument of x squared minus 3x. And what do we have now?
A polynomial.
Yeah, a quadratic polynomial. And how do we solve these?
You move 4 to the other side.
Yeah, set equal to 0 and then factor. So we end up with x squared here minus 3x minus 4 is equal to 0. And in this case here, what do we factor?
X minus 4,
X minus 4, x plus 1 equals 0. So we're going to get two x terms. X is equal to 4 and negative 1. And do we definitely want to do a check here?
Yes.
We definitely want to check here. So if we plug in 4, we're going to get log base 4 of 4 squared is 16 minus 4 times 3 is 12. That would be 4. And is that indeed equal to 1? That is. So that one checks. And for the other one, we would have log base 4 of negative 1 squared becomes positive 1. And then negative 1 times negative 3 is positive 3. So we would get 1 plus 3 is 4. So again, does that one check out?
Yeah.
Yes. So this one does indeed have the two solutions. Yes.
Is having the negative one okay since since the argument can't be negative?
Yeah, so the argument can't be negative, but that doesn't mean that you couldn't do, like let's say you had a situation where you had like a negative x in here is equal to, let's make up a number, 5, right? Because if we went to solve this, what would our solution end up being? It would be a negative value.
Okay.
Yeah.
And then also when you're checking, could you just plug that into the 4 to the first power equals x squared minus 3x, or do you have to plug it into the log?
You have to plug it into the original, log. Okay. Because again, if we just plug it into the exponential, we could end up with two solutions that do work for that. But again, you may end up with one solution that once you plug into the argument, makes it a negative and makes it false. Okay. Couple other properties here. So in the first one, I have log base b of b to the x power is equal to x. So the things we want to notice here are that the base of the log is equal to the base in the argument, and that the argument is being raised to another power. Okay. So if you have the base of the log and then the argument has the same base raised to another power, it's going to be equal to whatever your exponent is. So whatever this is. And in our next log lesson, we're going to talk about some other properties, and that actually makes this one make a lot more sense. But for now, we'll just know it as this property. And then the other property, we have b raised to a logarithm, right? So now the logarithm is inside the exponent, but that log has the same base as the, as the exponent that it's in, okay? And in this case, the same thing, the argument here, it's equal to that argument. So looking at our first example, I have 8 raised to the log base 8 of x. And so again, I want to notice that this base is equal to the base on the log that's in the exponent. Therefore, this term is equal to x, just the argument. In our next one, I have log base b, base 7 of 7 raised to the negative x. Right, so again, the base of the log is equal to the base in the argument, which means this whole piece is equal to negative 3x. And C, I have log base 2 of 64 to the x. What's changed here?
The base.
Yeah, they're not the same. However, do you notice a relationship between 2 and 64? It's 2 to the 6th. So we can restate this one as log base 2 of 2 to the 6th, which is then being raised to the x power, which then allows us to use that power to power rule. This becomes log base 2 of 2 to the 6x. And now my base of the log matches the base of this exponent. So this is equal to 6x. All right, our last one. I have e raised to the natural log of 20. Right, and so again, what do we recognize natural log to be? It's a base of e. So this is doing the same thing as doing e raised to the log base e of 20. And so again, the base of this is equal to the base on the log and the exponent. Therefore, this piece is equal to 20. Okay. So what do we think? Are we feeling a little more comfortable? Yeah? Okay. So that's all we have for the day. The homework is up here. I won't check it until the class after the quiz.